Welcome everyone, and today the first talk of our morning session is by Andreas about open and closed flux tube in the large and limit on the lattice, if I understand correctly.
So thanks a lot, Victor. I'm excited for for this workshop and for giving this presentation because I will show you some very fresh results I find exciting, and I think they go along with the purpose of this collaboration. And I think throughout this data we can shed more light on the physics of the flux tube and the confining string. So the work is basically based on three distinct works. The first one is the work on confining strings and the worksheet axiom in the lattice, where we mostly focus on the K equals 1 flux tube, on the fundamental flux tube. And hopefully the paper will be out anytime soon. So the next one is the spectrum of K equals 2 closed flux tubes. So just to give a very brief idea, so what we have studied so far is fluxes that emanate from the fundamental representation of color, but we can also construct fluxes, where the color emanates from different representations than the fundamental higher representations. And here we focus on the K equals 2 antisymmetric representation, where we can actually think of these flux tubes as flux tubes basically that wind twice around the torus, or flux tubes that wind once and they couple with each other. And finally, I will demonstrate some of the very new results on the spectrum of open confining strings in the large and limit. So this is the first ever, calculation of the excitation spectrum of the open flux tube in the large and limit. Okay, so very briefly, we know that using deep quarks are confined in bound states called flux tubes, and long flux tubes behave pretty much like thin strings. So if you pull apart the quark and the quark, the potential will rise linearly until at some point it breaks and we encounter the string breaking, and this is actually something that we can also observe on the lattice. So this is a lattice calculation from 2019 with an F equals 2 plus 1 fermions, where we can actually observe the breaking of the string. Here you see two lines because we have two kinds of mesons. Okay. So, however, in order to observe this string breaking, we need dynamical fermions. So, in our case, we just want to study the dynamics of the flux tube, and therefore, we want the string breaking effect to be suppressed, and the only way to do it is to work with the pure gauge theory, where, the vacuum cannot create quark anti-quark, okay, and create the string breaking, initiate the string breaking, and therefore we are safe by choosing the pure gauge theory. Formulation, we know that there are d-2 massless Goldstone modes from the broken translation invariance in the d-2 directions, and therefore we would expect to have an effective string theory describing the spectrum of the flux tube. Now the questions to be addressed is there such an effective theory? How good an approximation of such effective string theory is? And also we want to ask the question whether there are additional massive excitations along the flux tube. Of course, we already know that there are additional massive excitations. Now on the lattice, the idea is simple. We extract the spectrum of the flux tube and we check whether the spectrum of the flux tube can be reproduced by an effective string theory model. And we also want to see whether there is some striking difference with the string theory model, which basically indicates that there is, new information that should be encoded within the effective string theory. And there are actually two different setups. One can investigate on the lattice, the so-called closed flux tube or Torellon, where we have provided a lot of information so far, and the open flux tube, where, our colleague Michele Gazzelle has provided, enormous amount of information, especially for the ground state. However, the excitation spectrum is still under question, and we need to understand how that behaves. And there is no effective string theory capable of providing a good description for the open flux so far. So this is a question that should be addressed by the community, and especially, I think, by this collaboration. Now, the closed flux tube, it is, let's say, a quite attractive framework because there are no boundary terms. And there is a richer spectrum due to the flux compactification, okay? However, it is computationally expensive, and it is computationally expensive because if you want to extract the energy spectrum as a function of the length of the flux tube, whenever you want to extract an energy for a different length, you need to provide a different simulation, okay? You need to perform a different simulation because the length of the flux tube is equal to the lattice extent. While for the open flux tube, okay, we need to deal with the boundary terms. However, the computation is not so expensive because this calculation is based on evaluation of large Wilson loops, and we can create these large Wilson loops within one simulation, okay, within one calculation. And this is quite cheap in terms of computational time. Now, we're going to move to the larger limit. Why? Because we want to suppress all the pure gauge phenomena and focus solely on the string-like behavior of the flux tube. Now, so far, regarding the closed flux tube, we moved from, we have performed calculations moving from SU12 up to SU2 up to SU12. While for the open flux tube, there are several works that have been. Yes.
Can you explain what the pure gauge phenomenon mean? I mean, the actions gauge invariant. What's the pure gauge?
It's the standard Wilson action, which is gauge invariant. It doesn't include any fermions, just that. So what's the?
It's pure glue.
It's pure glue.
Okay.
So just as U3, in the continuum, this basically gives you the Young-Lewis action. Okay. Is this clear? Okay, good. So people mostly focus on SU3 because back then it was realized that the spectrum of the open flux tube is directly related to the spectrum of hybrid mesons. So they extracted the spectrum of SU3, but the spectrum of SUN goes to infinity. It's still unknown, okay? So, and actually in this work, the results that I'm going to present you, we have performed calculations up to SU6, which indicate that, there is a rich spectrum and also, a couple of axions lurking on the wordsheet of the flux. Now, the effective theory of long strings has been a question addressed, through the years. So this actually started being investigated in the early 80s by Lusher and Arvis. And it has evolved a lot, and mainly during the last 10 years. So we had the idea of TBA that came quite, recently, 10 years ago, by Dubowski, Gorbenko, So basically, we are able to identify the universal properties of the Qs in this string. Now, by imposing reparameterization invariance and d-dimensional target space Poincare symmetry, one can write the most general form of a bosonic action. I mean, these guys here basically vanish, and the subleading term appears at order ls to the power of 2, and therefore the perturbative perspectives of the theory can universally be determined by just the Nambu-Goto action. So, by quantizing the Nambu-Goto action, we see that for the closed flux tube, we see that the energy of the flux tube is given by this expression here, which is basically described by the number of left-moving phonons and right-moving phonons, and the winding momentum, which basically relates the number of left-moving phonons and the total contribution of left-moving phonons and the total contribution of right-moving phonons. And actually, if one performs the 1/r expansion, or the effective string theory by including higher derivative terms in the action, one can show actually that the energy of the flux tube should be the energy of Nambu-Goto plus a correction of 1/r to the power of 7. Now, similarly, for the open string, if you quantize it, if you quantize Nambu-Goto, you get the Arvis potential, or the Arvis energy, where the energy now is described just by the total contribution of left circularly polarized phonons and right circularly polarized phonons. Okay, so the basic excitation number is this guy here.
It's best to maybe not touch the screen. For the
Okay, so that's why. Okay, thanks. Okay, and if we expand the, if we make the 1/r expansion, we actually realize that the relation of the effective string theory to Nambu-Goto is that the energy is given by Nambu-Goto plus a leading term that appears at order 1/r to the power of 4, which is due to the boundaries, and also another term which is proportional to 1/r to the power of 5. However, for the purpose of this investigation, I will just focus on Nambu-Goto, since these are subleading terms. Okay, but let me tell you that these terms have been extensively investigated by Michele and also by Bastian Brandt. Okay, so we actually can identify these terms here with a very high precision. Okay.
Do I understand it correctly that this capital B and capital C, that is some calculable things, and this like little b bar, that is a free parameter?
Yeah, right? So this is a free parameter, this is calculable, which depends on the excitation of the string.
The capital C is related to boundary terms, or to the fact that you have considering also excited state?
No, it also depends on the excitation of state. Okay. Now, so these were like the first results that came out. Let's say, I mean, one of the first results that demonstrated that actually the spectrum of the flux tube can be approximated quite well by Nambu-Goto. This is 2 + 1 dimensions. This is the ground state, this is the first excited state, and this is the second excited state, which according to the Nambu-Goto should be two-fold degenerate. You see that there are 2 states here. And it's clear that these are actually the expansion in 1/r, okay? Leading order next to leading order and next to leading order. And you can actually see that none of these line approaches our data as good as Nambu-Goto. And this is clear by the expansion that I showed you before. However, we see that, as we move closer to the confining transition, or to very small flux tube length, we start getting deviations, okay? And this is actually, it was clear that this deviations were due to, let's say, could be investigated by expanding the softness of the phonons. So actually, one could perform two different expansions, one in 1 over R and one in terms of the momentum transfer. And this has actually led to the idea of using the thermodynamic ansatz, where, I mean, we actually investigate the finite volume spectrum of 1 plus 1 D integrable theory from 2 to 2 scattering. The leading spectrum is given by integrable theory of D minus 2 scalars with this phase shift. And actually using the TBA at leading order, this leads to the GGRT. And no wonder why GGRT, what I showed you here, works so well for the flux subspectrum. Now, the phonon scattering amplitudes can be calculated with perturbation theory. Actually, by diagonalizing the S matrix in this theory, one can extract the phase shift for spin 2 states, spin 0 states, scalar states, as well as the pseudoscalar states. Up to, I mean, and we see that the terms up to L to the power, LS to the power of 4 are, I mean, can be calculated analytically in perturbation theory, and one can also consider higher order in S, in momentum transfer. Okay, and this will play a role, as I will show you later in my results. Now, then it was shown that TD bar simplifies TBA because the Andreas theory is free in the leading order, and we can neglect all the winding corrections in the Andreas spectrum, and then the momentum quantization condition becomes the asymptotic Bethe ansatz, and the formula to work and compare our data to the effective string theory is to investigate the spectrum of phonons and massive excitations interactions using the asymptotic Bethe ansatz plus TD bar deformations. And I will show you results, I mean, how good this works. Now, I think one of the most important messages that came out from the lattice calculations was that there was I mean, a signal, a clear signal of a massive resonance. Okay. So a massive resonance, I mean, naively, you would think of it as a state which is coupled to the absolute ground state plus a constant term of the order of the mass gap. Okay. So, and it was clear that there was something new going on the theory. So Dubovsky et al. In 2013 included a massive resonance, the so-called axionic string ansatz, in the action. So they included a pseudoscalar field in the wordsheet axion, sorry, in the wordsheet, and this field was the axion. And from Monte Carlo data, in 4-dimensional SU3 Young mills, I mean, they could extract the mass of the axion, which is 1.85, and the coupling of the axion, which appears to be extremely close to the integrable. Okay. Now, let's go to the actual calculation and how we perform the calculation. When it comes to closed flux tubes, what do you actually do?
So that previous theory is integrable, or is there, that's not the TT bar?
Say again?
The previous one, the previous action you wrote, this is an integrable?
No, this.
But what is this Q integrable you're comparing to?
This is the Q that that derives if you assume that the theory is integrable.
For zero mass.
For zero
There is
mass.
integrable theory when mass is zero and with that value of coupling.
So how do we extract the spectrum of the closed flux tube? So we actually create Polyakov loops on the lattice, but instead of circulating this Polyakov loop along the temporal direction, we circulate, okay, we wind this, this flux tube along the spatial direction, like this guy here. And we take a flux tube and an anti-flux tube, okay? And we take correlations, separated by a Euclidean time t. And one can show that a correlation can actually, for t large, can project onto an exponential where the exponent can give you the ground state. And one can use the so-called effective mass to extract the ground state. This is, just a technical thing. However, this doesn't give access to the excitation spectrum. And in order to extract the excitation spectrum, you need to do something more sophisticated. It's called the variational technique. Okay. And very similarly to the open strings, now to the open, when we do with open strings, what we actually calculate is basically large Wilson loops. Okay. These are contractable loops on the lattice, which are separated by, so we have two spatial lines, okay? Let's say a flux tube and an anti-flux tube, which are separated by temporal Euclidean time t. And we can actually show that it will also give you the ground state, okay? In the st goes to infinity. And again, we need to use the variational calculation. So the variational calculation is quite, let's say, is not, is a way basically to perform the traditional variational calculation we do, in quantum mechanics. And the idea is that instead of having now a correlator, we do have a correlation matrix, okay? So we need to construct many of these operators, okay? And create the correlation matrix now, which we diagonalize, we extract the eigenvectors, extract the correlator for each state, and by fitting the results, we can extract the mass of each state. And this is the so-called generalized eigenvalue problem. Now the quantum numbers for the closed string is the spin and the parity, and we project onto 5 irreducible representations. We have 2 parities actually, and this gives in total 10 irreducible representations. And for the open flux tube, I use the standard nomenclature that has been used by lattice gauge theorists, for many years. The quantum numbers is the spin, which is the projection of angular momentum J onto the charge axis. We need to be careful here. Because I received this question, whether I also, because this could also rotate, around itself. No, this is not a rotating string. This is just a string with an intrinsic spin, okay? It's, there is a combination of parity and charge conjugation. And for spin 0, we also have an additional quantum number, which is the transverse parity. So in total, we actually have, I'm projecting, in this work, I project onto 8 different irreducible representations. So, and these are basically what one can use, these operators in order to create these flux tube operators. So we use these deformations. For instance, here, I gave an example of an operator that projects onto j equals 1. So you have to take these guys and rotate them so that you could project onto the right, let's say, spin or the right parity and so forth. And let's go and see some results now. So let's go and see what happens with a closed string, absolute ground state that corresponds to n left equals n right equals 0. The only information we can get out of these results is basically the leading correction to Nambu-Goto. So the way to do that is to fit the data. Here I provide data for SU3, SU5, and SU6. So you fit this data with Nambu-Goto for large enough strings. You extract the string tension, and then you can use this string tension to identify the leading correction, and the leading correction is found to be consistent with gamma equals 7, okay? So the subleading term, is in accordance with gamma equals 7, as we expect from the theory. Of course, one could argue that gamma, equals 5 could also work good. However, this to be, more precisely understood, we need much more statistics, okay? But still, I think it's really great that we could find this agreement with the theory.
What P is probability?
P is the p-value. It's. Now, and let's go and see I would say, the most interesting results that basically it was the turning point in understanding the existence of this axiom. So what you can see here are results for n left equals n right equals 1. This is SU3. I plot SU3 because SU3, are the most precise results. And the reason is that as we move to the larger n limit, computational time basically increases exponentially. Okay. What I didn't tell you is that from a practical point of view, going to the larger n limit is extremely difficult, and it's impossible to go above SU6. Okay? And the main reason is that we lose basically the ergodicity of the Monte Carlo simulations of the Markov chain. Okay? Basically, the topological charge gets frozen. Okay?
You showed something about SU2 to 12. So how did you go to SU12 then?
Okay, yeah, that's a good question. That's a very old calculation, and then there is the purpose of that calculation was to understand whether the axion mass would decrease to 0. That's why I moved up to SU12. But at the SU12, there we still had this issue. The topology was frozen. Okay. But we also performed calculations for several topological sectors, and we realized that the result was not affected. But you cannot extend that to, let's say, a calculation of the full spectrum. I think this is quite dangerous because CP odd sensitive quantities could be affected a lot by topological freezing. Okay. Of course, there is the risk. You can take the risk and perform calculations at frozen topological charge. Okay. Yeah,
So do I understand correctly that the matching with Nambu-Goto, even at very small r, basically works, right?
It works here.
No, for the ground state.
For the ground state, it works up to a correction of 1 over r to the power of 7.
At small r, right? At some point you should be hitting asymptotic freedom, right?
Well, okay. Yeah, that's a good question. So
it looks like the confinement sets in very early, basically.
The confinement sets very early, yeah.
But if you go beyond the confining regime, can you see the asymptotically free regime?
This is a closed string. There is no asymptotically free regime here. It's small radius.
It's a small radius.
Small radius center symmetry gets broken. It's not a quark potential.
No, but still, you should be seeing free gluons.
No. Actually, what would happen, Igor, is that once we hit the critical temperature or the critical length, basically we lose confinement. So basically, the flux tube dissolves.
If I can add a comment, in the open string case, if you go...
See the 1 over r log r.
You see, the one gluon exchange. Precisely.
Exactly, yeah.
Simulations, obviously, there is no effective string there.
The results that I will demonstrate for the open flux tube, there you can actually go to this, you can approach the perturbative regime quite close. Here, the tricky thing here is that as you approach the criticality, then basically the string starts filling the phase transition, and the critical exponents of the theory will set in, and actually the effective string theory stops becoming, being a good description.
Critical is when it becomes complex, right? The ground state energy.
Yes. Yeah. However, for SU2, which is a second order phase transition, you could go slightly above the transition. Okay. Yes, Alexei.
Confused. For SU2, it's supposed to be a second order phase transition.
Mm-hmm.
So that's exactly the case where I would think that continuing past the transition would be bad. Where after a first order transition, you could go to supercritical regime and go a little bit past, right? Because you're going to get into a metastable phase. So I thought it would be the opposite. With the first order transition, you could go a little bit past the phase transition temperature. Before
Well, in SU2 you can cross the critical temperature.
with SU2 you can, but it's a second order phase transition.
It's a second order phase transition, yeah.
You cannot supercool or superheat second order phase transitions. You can do it for first order, not for second order.
Well, in first order phase transition, you just have, for the SU3, SU3 is with the first order, and SU4 is first order phase transition. And I think that's where, I mean, the transition is how do you call it, is strong. I mean, okay.
It gets stronger with
It
that.
gets stronger, yeah. So you can actually cannot go beyond this critical temperature.
I can clarify what I mean.
Yeah, we can discuss
It's not
later.
important.
Yeah, I'm running out of time. Okay, and I still need to show you a lot. So, okay, I mean, in this plot, what we actually see is that according to Nambu-Goto, this should be fourfold degenerate. We have a state with 0 plus plus, 2 plus plus, and 2 minus plus, and these states appear to be very close to Nambu-Goto, while there is a state of 0 minus minus, which has huge deviations from Nambu-Goto. So there was a question of is this state, let's say, an axion, a massive excitation, or is this a state which can be thought of as a flux tube and a glue ball? I mean, coupled. The way to investigate that is to move to the larger limit. If it's a coupling between a flux tube and a glue ball, you expect that this will be suppressed. It doesn't get suppressed. This is SU3 after SU6. And if I actually subtract the absolute ground state, we see that this is a line, okay? And so there is a plateau. And if I compare it with SU3 and the result that Sergey extracted based on my old results with Mike, I mean, you see that this is 1.85. This is the mass of the axiom, okay? Now, let's switch on the axionic ansatz, and let's also include the phase shift due to the inclusion of the axion. So, using the TD bar deformation of the asymptotic Bethe ansatz, or the TBA, we can actually fit the results using the 0 minus minus and the 2 plus plus or the 2 minus plus. Here, I mean, we need to be careful. I mean, we expect to have parity degeneracy, but on the lattice, this parity degeneracy is slightly, it could be broken due to lattice artifacts. But at the continuum, I mean, this degeneracy should become exact, okay? I mean, this is a property of the rotational symmetry. By fitting these states here, you can see that we get deviations from the Nambu-Goto, from GGRT, for the 2, spin 2, and the spin 0 plus plus. And you can see that the line for the 0 plus plus actually provides a much better description for our data, okay? So this data has not been used to fit any parameters, okay? And if you compare SU3, SU5, SU6, you can see that the mass of the axion is slightly, let's say, depend on the n, okay? So it basically acquires a more or less constant value around 1.65. Now, if I go to the 0 minus minus state, where we have the axion, and I use the TBA with no higher orders of momentum transfer to predict, let's say, the spectrum, the energy state of this state here, which has 2 phonons with opposite momenta, but the momentum is large. You can see that we get this dashed line, which it looks nothing compared to the data, but if we switch on higher orders in momentum transfer, we see that the results, appear to provide a very good description for the data. And if we move one state further up and we apply the asymptotic Bethe ansatz and the TD bar deformation, we can extract this line here, which approximates our data quite well. So it looks like we do have an effective string theory that can describe. Now, if we go to the 0 plus plus states, This is the state, this is absolute ground state, the first excited state I showed you. And this is the second excited state. And actually, if I subtract the absolute ground state from this state here, we see that this looks like a plateau. And if I focus on SU3 and beta of 6.0625, this plateau actually is equal to 2 times 185, which is the mass of the axion. So it looks like we also have a coupling between 2 axions. And if we perform the TBA analysis, we actually see that without the TD bar deformation, we get this dashed line here. And when we switch the TD bar deformation, the interaction between the 2 axions, basically, we end up having this line here, which approximates our data quite well, and actually leads to the conclusion that the interaction between the axion is repulsive. Okay, so having said, having shown you the results for the fundamental, let's go and see something, I would say a bit more exciting, because I don't understand the data here. Okay? It's, sorry, yeah, we still need to understand, a lot of things. So for SUN larger than 4, equal to 4, there is a possibility of having stable strings which join test charges in representations higher than the fundamental. And we can label this by the way the test charge transforms under the center of the group. And we call, these strings K strings because they have an analytic K. Now the K equals 2 fundamental, the K equals 2 anti-symmetric representation can be built by taking the tensor product of 2 fundamental representations. And this will give us a symmetric and anti-symmetric. And there is a way to actually construct this on the lattice. Now, a K string can be thought of as a bound state of K fundamental strings. So if you have like K equals 2 fundamental strings, you can think of them binding, experiencing some repulsion and some attraction, okay? Now, the operators for closed flux tubes, can be calculated using this formula here. Forget about the formula, we just tell you that for K equals 1, the simplest way to construct, the way to construct an operator that projects onto K equals 1 state, it's just by creating a Polyakov loop that wins only once around the torus. Now for K equals 2, there are 2 ways. Either you construct an operator that wins, it's a Polyakov loop that wins twice around the torus, so you take the path order product of links around the torus twice, okay? Or you just construct a K equals 1 flux tube that wins once and square it, okay? You take the trace of U squared. Now, in order to project onto the K equals 2 antisymmetric, basically you need to take the linear combination of this guy minus this guy, okay?
Maybe to speed up a little.
Yes, okay. Yeah, okay, so this is the absolute ground state. Okay, you can see that this is Nambu-Goto-like, where the string tension is the K equals 2 antisymmetric. And the interesting phenomenon comes here, where again I plot results for the first excited state, and right equals 1. And you can see here, this is the 0 minus minus, which again it looks like an excitation. A massive excitation on the absolute ground state. Here I get the first excited state of 0 plus plus, which again looks some kind of excitation, as well as the ground state of the 2 plus plus, which also looks like an excitation, while for the ground state for 2 minus plus appears to be quite close to the Nambu-Goto line. What is striking here is that these 2 states, although they should be degenerate on the lattice, they have this huge splitting. So the first thing that we wanted to ask is whether this was due to lattice artifacts, but if I reduce the lattice spacing, actually I get the same shift, okay? The same separation. So it looks like this is a continuum effect, okay, which is puzzling. One would expect to have a degeneracy. I also increased the volume by 1/5 times the volume. And it looks like this discrepancy is still there, just to check if it's finite volume effects. Now, if I go to the large, if I move closer to the large N and do SU5, you can see that, I mean, this discrepancy becomes more striking. And if I subtract the absolute ground state, you can see that the 0 minus minus state appears to be consistent with the axion mass, okay, from the k equals 1. So it looks like there is a universality here regarding the mass of the axion, while I mean, the 0 plus plus and the 2 plus plus states become degenerate. And they look like there is some kind of excitation, possibly due to the coupling of the two fundamental strings. Okay? And now let's go, I mean, if I have a couple of minutes, I can show you results for the open flux tube in SU6. It won't take too long. So for sigma G plus, this is the absolute ground state, okay? This is the first excited state. Okay, you can see that we have two phonons here. I mean, we have some deviations. But we also get a plethora of states. I think we have enough information, I think, for a good determination of the phase shifts in a TBA analysis. Okay. So similarly, for S sigma G minus, here I get, this is the ground state, the first excited state. They appear to be degenerate. These states could be, I mean, one of the states could be of spin 0 and the other state which could be of spin 4, because the representation doesn't make, I mean, it includes both j equals 0 and j equals 4. And you can see that this also looks a bit like, I mean, some kind of axionic behavior. It has some axionic behavior. If I subtract the absolute ground state, I get this behavior that looks, I mean, looks quite axionic, okay? With a mass of around 2. So possibly there is an interaction with an axion here. This is the sigma U plus. Again, you can see that we have deviations, large deviations from Lamb-Bogotto. And this is the sigma U minus that I think is the most interesting plot that I show you, because all the lines, I mean, look to be increasing linearly with R. So it's the ground state plus a constant term, okay? And if I subtract the absolute ground state, the ground state, okay, is this guy here with a mass of 1.66, okay? And if I compare it with the mass of the axion that we extracted from the closed string, we get 1.656 with an error of 2. So it's clear that the open flux tube includes the axion that we also observe in the closed flux.
The quantum numbers of the states?
0 minus minus.
All of them?
All of them, yeah. All of them are 0 minus minus. Good. I mean, okay, the rest is just, I mean, similar plots where, I mean, you can see again the determination of the spectrum. Here we get smaller deviations from Lamb-Bogotto, mainly because we just have one phonon on the state. Here we get actually nearly 0 deviations from Lamb-Bogotto. We just have one state with one phonon. Okay, it's quite similar to what we observe in the closed flux tube. This is the delta. I mean, we get a similar, I mean, behavior, and this is the delta U. Again, we get a similar behavior. What is missing here is an effective string theory capable of providing good results for the open flux tube. Okay, so let me conclude. We have obtained the spectrum of closed flux tube in 4 dimensions. Okay, the interaction involving axions can be approximated by the TD bar deformation, and we actually observe 2 towers of states, one tower with phonons and one tower with axion and phonons. We have obtained the spectrum of open flux tubes in 4-dimensional SUN gauge theories. Again, the spectrum involves an axion with the same mass of the with that of the closed flux tube, and there is the need of an effective string theory for open flux tubes. We have obtained the spectrum of closed k equals 2 strings in 4-dimensional SUN gauge theories. We still need to understand a lot. Actually, the splitting between 2 plus plus and 2 minus plus is quite, I would say, disturbing. I don't have a clue, I mean, why that splitting is there, and we need the TBA analysis for the open flux tube, okay, in order to understand the spectrum. If you remember, the K-2 flux tube spectrum and the open flux tube spectrum was a promise that I gave you last meeting. So what to promise next is the spectrum of the flux tubes in the n=1 supersymmetric theory on the lattice with my colleague Georg, and also the spectrum of the flux tube when we add adjoint fermions in SU2. Again, this is a project I do in collaboration with Georg Beckner, Biagio Lucchini, Ed Bennett, and Pietro Butti. So, thanks a lot for your attention.
There's a K-dependence of the string tension.
Exactly, yeah.
And do you see that?
We see the string tension depends depends on the K. Yeah,
Right.
This we can see. This is, yeah, I didn't comment on that. It's
There's a naive prediction, of course.
there is a naive prediction. There are actually two predictions. There is the Casimir scaling
Yeah.
and the sine rule. And
The Casimir I know, but what's the other?
I think the Casimir, the Casimir, yeah, and there is the sign prediction which came from, I think this was work of Schiffman and Adi Armoni.
What is it? What do you mean?
No, it depends on
I think the question is whether it goes like 1/n or 1/n squared, the body.
yes, exactly, yeah. So
There were some arguments that it
Okay.
is only allowed to go as 1/n squared, but I think it really should go as 1/n because of mixing between.
I think it's neither 1/n squared, it's nor 1/n. I think somewhere between. Yeah, you can. This was.
Anyway, what do you see?
Well, at this calculation, I just have two values of n. I can't not perform a decent.
Very interesting to
This is
study
not-
1/n power. Because
Yeah. Okay, but this has been observed in 2+1 dimensions. We have carried out this.
on 2+1, it seemed a very close fit to Casimir, right? If I remember.
It's extremely well. It's closer to Casimir instead of the sign prediction. But the thing with the Casimir scaling is that Casimir scaling can also provide predictions for unstable flux tubes. Okay, for instance, here, in 2+1 dimensions, we could also extract highly unstable flux tube spectra, like the K-2 symmetric representation, and there, or the K-3, for instance, anti-symmetric mixed representation and symmetric, and there we saw that for the mixed representation and the symmetric, the string tension is actually consistent with the Casimir scaling.
Have you looked beyond K? You're doing SU6, you could go to K=3, 4.
Okay. In the large n limit, you expect that the first approximation one would expect is that you have the string tension is close to 3 times the fundamental string tension, which means that the mass basically increases linearly. And from a practical point of view, this is almost impossible to do it at these lattice spacings. So for SU6, for 2+1 dimensions, you can do. For 3+1 dimensions, I think it's almost impossible with the current technical, let's say, capabilities. It's impossible because you need to go to very small lattice spacings to be able to see these massive flux tubes. Also, one could also go to adjoint representation, but also the adjoint representation is extremely massive, so you cannot extract this.
So for your splitting between 2± and 2++, well, the only possible theory explanation is that parity gets spontaneous with volume somehow.
Yeah, I would say the parity.
But then you should see another ground state closely degenerate, right? Then it should be, and there is no sign of
Yeah,
that.
there is no sign of other ground states. Yeah. it's puzzling. I don't know.
It doesn't seem like there is an explanation.
Yes. I mean, and I think also it's quite interesting the fact that it's becoming. I mean, I don't know. It's becoming. I mean, degenerate with the. I mean, 0++ and 2++ become degenerate. It's quite puzzling. I really don't understand. Yeah, I hope that I mean we can discuss this and we can.
Very roughly speaking, the string, you're basically seeing deviations from non-Bogota, but this composite string is a more complicated object. It's kind of thicker. Right?
Yeah, you can think of, let's say, a resonance between two fundamental.
Like it separates out into two. It's sort of weakly bound.
But that's just consequence of symmetry, that 2++ should be degenerate with 2 minus plus, right?
Yeah, so this is like the well, let's say the string theoretical, I mean, way of thinking. But on the lattice, I mean, where you have like the SO2, I mean, okay, I mean, it's not exactly SO2 because you have rotations over pi/2, but you would expect to have exact parity symmetry as you move, parity degeneracy as you move closer to the continuum.
Just O2, it's a spin,
Yeah.
spin 2 representation of O2, so the 2 here is a component.
Yeah, you have the,
O2 is
exactly.
reserved, the exact.
So yeah, it's quite puzzling. I mean, I think it's the most interesting, I mean.
How close are you to the continuum with this value of beta?
Well, that's a good question. Okay. This is SU5 and beta of 18.3375. Okay. And this is the same beta as the beta I used. Let me see. No, I don't have the result here. As the beta I use actually for the k=1 string, as you. Let me see if I have it here, but I also have it in other plots. No, I don't have it here. Maybe I mean it's around. I mean, let's say if we compare it to the equivalent and to the equivalent beta of SU3 is around 0.9 Fermis. It's quite close to the continuum. And for k=1, we actually see that the deviation between these two states, the 2++ and the 2- plus, is around 1 sigma. Okay. In some cases, I mean, they agree within the errors, and in some other, I mean, due to fluctuations, I mean.
It's still a bit strange that it's within 1 sigma, but it's systematically one state is always heavier than the other, so it doesn't look like.
Yeah, the 2- plus is always heavier.
It looks like
yeah.
a systematic effect there, but
Yeah,
it's much smaller.
yeah, you can see here the 2- plus is the magenta point is always slightly higher than the 2++. So it looks like a systematic effect. Yeah.
Well, it could be going to 0, maybe.
Hopefully.
You mean going to zero lattice spacing?
Right.
Yeah.
This is, yeah, I mean, it is hard, but it's something that can be investigated consistently. Maybe one can focus on these masses and perform a consistent calculation in the continuum limit. Yeah. So but again, I mean, one has to bear in mind that these are massive excitations, massive states. So it's not easy to identify those masses. One should do something more sophisticated, maybe go to anisotropic lattices, where you would have more time resolution in order to fit your data. And actually, this is what we do for the open flux tube. We did like if you see for the open flux tube, in order to get these results, we actually applied. You can see these numbers here. This is psi cos 4 is actually is how anisotropic the lattice spacing is. So actually, the time resolution is 4 times smaller than the space resolution. Okay, and that's what enables us to extract, so many states in this in this.
But for K equal 2, that splitting is huge, right? It's like 5 sigma.
Yeah, no, for K equals 2, that's 5 sigma, it's, yeah. But okay, I mean, one can invest effort and identify the continuum.
Okay, let's thank Andreas again. Continue the podcast.
Go away.